What if our universe isn't alone? What if everything we can see, everything we've ever observed with our most powerful telescopes, every galaxy and star and planet scattered across billions of light years of space, what if all of that is just one universe among countless others? What if there are other universes out there, perhaps infinitely many of them, each with its own stars and galaxies, or perhaps with completely different laws of physics, different properties, different histories? This isn't science fiction. This is a serious question that scientists and philosophers have been asking for decades. The idea of multiple universes, what we call the multiverse, has gone from wild speculation to legitimate scientific theory, debated by some of the smartest minds in physics and cosmology. And tonight, we're going to explore this profound question together. How many universes are there? Is our universe the only one, or are we part of something much, much larger? If you're new here, welcome to the Sleepless Astronaut channel, where we explore the deepest mysteries of existence while you drift peacefully toward sleep. If you enjoy journeys through cosmic questions like this, consider subscribing so you never miss an exploration into the unknown. We make these videos to help you relax while expanding your mind with the universe's most profound puzzles. Tonight, we're going to discover that the multiverse isn't just one idea, but many different ideas, many different ways that multiple universes could exist. Some of these ideas are based on well-established physics. Others are more speculative, pushing the boundaries of what we can know. And all of them will change how you think about reality, about existence, about your place in the cosmic scheme of things. So settle in wherever you are. Get comfortable. Let your body relax completely into whatever surface supports you. We're about to explore one of the biggest questions anyone has ever asked. And as we explore it together, you're going to feel your mind expanding while your body sinks deeper into rest and peace. The question of whether other universes exist is ancient, far older than modern science. Human beings have been wondering about this for thousands of years, asking whether our world is the only world, whether reality extends beyond what we can see and touch and experience directly. Ancient Greek philosophers debated this question. Some argued that our cosmos must be unique, that there could only be one universe, one reality, one existence. Others suggested that there might be many worlds, perhaps infinitely many, each separate from ours, each with its own properties and inhabitants. These were philosophical arguments, thought experiments, not based on observation or experiment, but on logic and reasoning about the nature of existence itself. For most of history, this remained purely philosophical. There was no way to test whether other universes existed. We could barely understand our own universe, our own world. The idea of multiple universes was interesting to think about, but it seemed impossible to ever know the answer. It was a question beyond the reach of science, something that could be debated endlessly without ever finding resolution. But in the 20th century, something changed. Physics advanced dramatically. We developed new theories about how the universe works, about space and time and matter and energy. Einstein gave us relativity, showing that space and time are flexible and connected. Quantum mechanics revealed the strange behavior of particles at the smallest scales. Cosmology became a real science, allowing us to study the universe's origin and evolution. And as our understanding deepened, the multiverse idea kept appearing, not as philosophy anymore, but as a natural consequence of our best scientific theories. Different branches of physics, working on completely separate problems, kept arriving at the same conclusion. Our universe might not be alone. Multiple universes might not just be possible, but inevitable, a necessary consequence of the laws of physics as we understand them. This was shocking to many scientists. The multiverse seemed too strange, too wild, too impossible to take seriously. How could we ever test it? How could we ever observe other universes if they're separate from ours? Isn't science supposed to deal with things we can observe and measure? If other universes are forever beyond our reach, what's the point of even talking about them? But other scientists argued that we should follow the math wherever it leads. If our best theories predict multiple universes, if the multiverse falls naturally out of equations that successfully explain everything we can observe, then we should take it seriously, even if we can't directly observe other universes. The multiverse might be real whether we can see it or not. This debate continues today. The multiverse remains one of the most controversial ideas in all of science. Some physicists embrace it enthusiastically. Others reject it entirely. Still, others remain uncertain, waiting for more evidence, more theoretical development, clearer answers to difficult questions. But regardless of whether the multiverse is real, thinking about it is valuable. It forces us to confront deep questions about the nature of reality, about what we can know, about the limits of science, about what it means for something to exist. And that's what we're going to do tonight. We're going to explore different multiverse ideas, understand where they come from, and think about what they mean for our understanding of existence. Before we dive into specific multiverse theories, we need to be clear about what we mean by universe. This might seem obvious, but it's actually subtle and important. What exactly is a universe? Where does it end? How do we define its boundaries? The most straightforward definition is that a universe is everything that exists, everything that's real, all of space and time and matter and energy. By this definition, there can only be one universe, because it includes everything by definition. If something exists, it's part of the universe. If it's not part of the universe, it doesn't exist. So talking about multiple universes becomes contradictory. If there are multiple universes, they're all part of one bigger universe that contains all of them. But this definition isn't very useful when we're talking about multiverses. So physicists use a different definition. A universe in the context of multiverse theories is a region of space and time that's causally connected, where events can influence each other. Our universe, by this definition, is the region of space and time that we can potentially interact with or observe, the region where causes and effects can propagate. This gives us a clearer boundary. Our universe includes everything we can see, everything we can potentially see in the future, everything that's close enough that light has had time to reach us, or could reach us eventually. It's defined by the speed of light and the age of the universe, by how far light and other influences can have traveled since the Big Bang. Beyond this boundary, there might be other regions of space and time that are causally disconnected from us. Events there can't affect us. We can't observe them. Signals from those regions will never reach us. These regions, if they exist, would be separate universes by our definition. They're real. They exist somewhere in space and time, but they're forever beyond our reach, completely isolated from our experience. This might seem strange. How can something be real if we can never observe it or interact with it? But think about it this way. 1,000 years ago, people in Europe had no idea that the Americas existed. The two continents were causally disconnected in practice. Nothing happening in Europe affected the Americas, and nothing in the Americas affected Europe. They might as well have been separate universes from the perspective of people living in either place. But of course, both continents were real. They both existed in the same physical reality, on the same planet, even though people on one continent couldn't observe or interact with people on the other. Eventually, travel became possible, and the continents were no longer isolated. But before that, from the perspective of any individual, the other continent might as well not have existed. It made no difference to their lives. The multiverse idea is similar, but on a cosmic scale. There might be regions of reality that exist, but are causally disconnected from us. Regions we can never observe or visit or interact with in any way. These regions would be separate universes by our definition, not because they're made of different stuff or follow different laws necessarily, but simply because they're beyond our reach. Now, here's the profound question. How many such universes might there be? One? A few? Infinitely many? And do they all follow the same laws of physics as ours? Or could they have different properties, different constants, different rules governing how reality works? These questions lead us to different levels or types of multiverse, different ways that multiple universes could exist. Physicists have identified several distinct multiverse theories, each based on different physics, each suggesting different answers to how many universes there are and what they're like. Let's start with the simplest multiverse idea, what's sometimes called the Level 1 multiverse or the infinite space multiverse. This is based on a straightforward observation about our universe and its possible extent. We live in what we call the observable universe, the region of space from which light has had time to reach us since the Big Bang. This region is enormous, about 93 billion light-years in diameter, containing perhaps 2 trillion galaxies. It's everything we can see, everything we've ever observed, everything we could potentially observe with our telescopes. But here's the key question. Does space end at the edge of the observable universe? Is there a boundary out there where space simply stops existing? Or does space continue beyond what we can see, extending farther, perhaps infinitely far? There's no reason to think space ends at the edge of what we can observe. The observable universe is just limited by how far light has traveled since the Big Bang. It's a horizon, similar to how you can only see a certain distance to the horizon when you're standing on Earth's surface. Beyond the horizon, Earth continues. You just can't see it from where you're standing. Similarly, beyond our cosmic horizon, space probably continues. There are probably more galaxies out there, more stars, more planets, all beyond the limit of what we can ever observe, because light from those regions hasn't had time to reach us yet, and might never reach us if the universe's expansion carries them away faster than light can travel toward us. If space continues beyond our observable universe, the natural question is, how far does it continue? Does it go on for a while and then stop? Or does it extend infinitely? If space is infinite, if it goes on forever in all directions, then we get our first multiverse. Not because there are different universes with different properties, but because an infinite universe would contain everything that's possible, including infinite copies of our observable region. Let me explain why this is true. In our observable universe, we have a certain amount of matter arranged in a certain configuration. Galaxies here, stars there, planets in certain orbits, atoms arranged in specific ways. There are many possible configurations of matter, many ways that atoms and molecules could be arranged. But the number of possible configurations, while enormous, is finite if we're talking about a finite region of space. Imagine you have a box containing 1,000 particles. How many different ways can you arrange those particles? A huge number, far more than you could ever count, but still a finite number. There are only so many possible positions each particle can occupy. Only so many possible arrangements of the whole system. Our observable universe is like a very large box containing a huge number of particles. The number of possible arrangements is mind-bogglingly large, far beyond anything we can meaningfully comprehend, but it's still finite. If you could count all the possible ways to arrange all the matter in our observable universe, you'd get an enormous number, but not an infinite number. Now, if space is infinite, then it contains an infinite number of such regions, each the size of our observable universe. Most of these regions would be different from ours. They'd have galaxies in different positions, stars with different properties, planets in different configurations. But if you have infinitely many such regions, and each region has only finitely many possible configurations, then eventually every possible configuration must repeat. This is a mathematical necessity. If you have infinite opportunities and finite possibilities, every possibility must occur infinitely many times. It's like rolling dice. If you only have 6-sided dice, you can only roll numbers 1 through 6. If you roll the dice infinitely many times, you'll roll every number infinitely many times. You can't avoid it. Applied to the universe, this means that somewhere out there, far beyond our observable universe, there must be another region exactly like ours. Same galaxies in the same positions. Same stars, same planets, same Earth with the same continents and oceans, same cities, same buildings, same people living the same lives, an exact copy of everything we know, perfect down to the atomic level, and not just one copy. Infinitely many copies. Scattered throughout infinite space are infinitely many regions identical to ours. Each one containing people identical to you, living lives identical to yours, thinking the same thoughts, making the same choices, experiencing the same experiences. This is a bizarre and profound idea. It means that right now, somewhere unimaginably far away, there's another you reading these exact words, thinking these exact thoughts, living a life perfectly identical to yours, and another you, and another infinitely many you scattered throughout infinite space. It also means there are near copies of you, regions almost identical to ours, but with tiny differences. Maybe in one region you wore a different shirt today. In another, you had eggs for breakfast instead of cereal. In another, you chose a different career. In another, you were never born because your parents never met. Every possible variation exists somewhere if space is infinite and filled with matter. This isn't science fiction or speculation beyond what physics allows. This is a straightforward consequence of infinite space combined with finite possibilities. If the universe is truly infinite in extent, then everything that can happen does happen infinitely many times, scattered throughout the infinite expanse. Of course, We don't know for certain that space is infinite. It might be finite but unbounded, curved back on itself like the surface of a sphere, where you could travel in a straight line and eventually return to your starting point without ever hitting an edge. Or it might be finite with some kind of boundary or edge, though this seems less likely based on what we observe. Current observations suggest that space is either infinite or so large that it's effectively infinite for all practical purposes. The universe appears to be flat or very close to flat on large scales, which is consistent with infinite extent. But we can't prove it's infinite. We can only say it's consistent with our observations and with our best theories. If space is infinite, then the level 1 multiverse is real. There are infinitely many regions beyond our observable universe, infinitely many other realms we can never see or visit or interact with. And among those infinitely many regions are infinitely many perfect copies of our observable universe, each one a separate universe by our earlier definition, because they're causally disconnected from us. How many universes are there in the level 1 multiverse? Infinitely many. More than that, there are infinitely many copies of our exact universe, and infinitely many variations of our universe with different configurations of matter. The number is beyond comprehension, beyond any meaningful counting or description. And yet, in some sense, these aren't really different universes. They're all part of the same space, all following the same laws of physics, all made of the same kinds of matter and energy. They're just far apart, beyond each other's horizons, unable to interact. They're like different continents on an infinite planet, separate but part of the same overall reality. This is the simplest multiverse idea, and already it's mind-bending, but it's just the beginning. There are other multiverse theories that are even stranger, suggesting not just infinite copies of our universe scattered through infinite space, but genuinely different universes with different properties, different laws, different fundamental characteristics. Let's move to the next level, what's called the level 2 multiverse, or the bubble universe multiverse. This idea comes from a theory called eternal inflation, and it suggests that our universe isn't just one region in an infinite space, but one bubble in an infinite sea of bubbles, each bubble potentially having different laws of physics. To understand this, we need to talk about inflation, a theory about what happened in the very first fraction of a second after the Big Bang. According to inflation theory, the early universe underwent a period of incredibly rapid expansion, growing from subatomic size to perhaps as large as a grapefruit in an unimaginably brief instant. This inflation was driven by a special kind of energy field that filled space, and as space expanded, this energy eventually converted into ordinary matter and radiation, creating the hot, dense state we call the Big Bang. Inflation explains several puzzles about the universe, like why it's so uniform on large scales and why it's geometrically flat. It's a well-supported theory that most cosmologists accept. But here's where it gets interesting. Once inflation starts in one region, it might not stop everywhere at once. In most of the inflating space, inflation continues, driving further expansion. But in some regions, random quantum fluctuations cause inflation to end, and those regions stop expanding rapidly and transition to the normal Big Bang expansion we observe in our universe. These regions where inflation ends become bubbles, little pockets of normal space embedded in a larger inflating background. And our universe, everything we can observe, would be one such bubble. Inflation ended here about 13.8 billion years ago, and since then our bubble has been expanding normally, cooling and forming galaxies and stars and planets. But outside our bubble, inflation continues, and in that inflating space, more bubbles keep forming as inflation randomly ends in different regions. Each bubble becomes its own universe, its own domain with its own Big Bang, its own history of expansion and cooling and structure formation. This process is eternal. Inflation never completely ends. It keeps creating new bubbles forever, an endless proliferation of universes budding off from the inflating background. The number of bubble universes is not just large, but literally infinite, with new bubbles constantly forming in the eternally inflating space. This is already remarkable, but it gets stranger. The bubbles might not all be the same. They might have different properties, different laws of physics, different fundamental constants. And the reason has to do with how the laws of physics are determined at the most fundamental level. In our universe, physics is governed by certain constants and parameters. The strength of gravity, the mass of the electron, the speed of light, the charge of a proton. These numbers seem arbitrary. They're not derived from anything deeper. They're just measured experimentally, and we plug them into our equations. But why do they have the values they have? Why is gravity this strong and not stronger or weaker? Why does the electron have this mass and not a different mass? We don't know. These constants just are what they are in our universe. But according to some theories, particularly string theory, these constants might not be truly fundamental. They might be determined by how extra dimensions of space are configured, and different configurations could lead to different values of the constants. If this is true, then different bubble universes could have different configurations, different values of the fundamental constants, different laws of physics. In some bubbles, gravity might be much stronger than in ours. In others, it might be much weaker. Some bubbles might have different numbers of particle types. Others might have different forces entirely, things we've never imagined. Most of these bubbles would be lifeless and uninteresting. If gravity is too strong, matter collapses immediately into black holes, and stars and planets can't form. If it's too weak, matter never clumps together enough to make stars. If other constants are even slightly different from their values in our universe, chemistry doesn't work right. Atoms can't form, or stars can't fuse hydrogen, or planets can't exist. The conditions for life, or even for interesting complexity of any kind, are very narrow. Our universe appears to be fine-tuned, with constants set to values that allow stars and planets, and chemistry, and life. This fine-tuning has puzzled physicists for decades. Why is our universe so special? Why are the constants just right? The bubble multiverse offers an answer. If there are infinitely many bubble universes with different constants, then most of them are indeed lifeless and boring. But some, by pure chance, have constants that allow complexity and life. We find ourselves in one of those special bubbles, not because our bubble is objectively special, but because we couldn't exist anywhere else. We're here because this is one of the rare bubbles where life is possible. This is called the anthropic principle, the idea that we should expect to observe a universe compatible with our existence because we couldn't observe a universe incompatible with our existence. It's not a deep explanation, but it does resolve the fine-tuning puzzle if the multiverse is real. Our universe isn't special. It's just one of the rare bubbles that happened to get lucky with its constants. How many universes are there in the level 2 multiverse? Infinitely many, continuously being created as inflation proceeds eternally. And among those infinite bubbles, there would be infinite varieties, countless different combinations of physical constants and laws, creating a vast landscape of possibilities. And here's something important to understand. These bubble universes are truly separate from ours in a way that level 1 universes aren't. In the level 1 multiverse, the other universes are just far away, beyond our horizon, but they're in the same space and follow the same laws. We could potentially travel to them if we had infinite time and faster than light travel. But bubble universes from eternal inflation are separated by eternally inflating space. The space between bubbles is expanding so fast that nothing can cross from one bubble to another. Each bubble is causally isolated, a completely separate domain. You can't travel from our bubble to another bubble any more than you can travel to before the Big Bang. They're not just far away, they're unreachable in principle, separated by space that's expanding faster than light can cross it. So the level 2 multiverse gives us infinitely many universes that are genuinely different from ours, with different physics, different properties, different possibilities for what can exist and how things behave. It's a vastly richer and stranger multiverse than the level 1 version. Now let's turn to a third type of multiverse, one that comes from quantum mechanics rather than cosmology. This is the level 3 multiverse, sometimes called the many worlds interpretation or the quantum multiverse. Quantum mechanics is the physics of the very small, describing how particles and atoms behave. And one of the strangest features of quantum mechanics is superposition, the idea that a particle can be in multiple states at once until it's observed or measured. The most famous example is Schrödinger's cat, a thought experiment where a cat in a box is both alive and dead simultaneously until you open the box and look. This sounds absurd, and Schrödinger proposed it to show how ridiculous quantum mechanics seems when applied to everyday objects. But at the particle level, superposition is real and well verified by countless experiments. An electron can be in multiple positions at once. A particle can spin in multiple directions simultaneously. These aren't just uncertainties about where the particle really is. According to quantum mechanics, the particle genuinely exists in all these states at once, in a superposition, until a measurement forces it to choose one state. But what happens when you make a measurement? The traditional interpretation says the superposition collapses. All the possibilities vanish except one, and that's what you observe. The electron was in many places, but when you look, it's suddenly in just one place, and the other possibilities disappear. But there's another interpretation proposed by physicist Hugh Everett in the 1950s. Instead of collapsing, the superposition continues. When you measure the electron's position, the universe splits. In one universe, you see the electron here. In another universe, you see it there. Both outcomes happen, but in separate, parallel universes. Every time a quantum measurement occurs, every time a particle's state is determined, the universe branches. One version continues with this outcome, another version continues with that outcome. And this happens constantly, everywhere, at every moment, because quantum measurements are happening continuously throughout the universe. The result is an unimaginably vast tree of branching universes, with new branches forming every instant. Every possible outcome of every quantum event actually happens, but in different branches. There's a branch where the electron went left and a branch where it went right. A branch where the atom decayed and a branch where it didn't. A branch where you made this choice and a branch where you made a different choice. This means there are versions of you in countless parallel universes, living slightly different lives. In some, you made different choices today. In others, you chose a different career years ago. In others, chance events turned out differently, leading to radically different life trajectories. Every possible version of your life that's consistent with quantum mechanics actually plays out in some branch of the multiverse. How many universes are there in the quantum multiverse? An incomprehensibly vast number, growing exponentially every moment as new branches form. It's not infinite in the same sense as the other multiverses. It's discrete, countable in principle, but the number is so enormous that it might as well be infinite. Every quantum event throughout the entire universe creates new branches, and quantum events are happening everywhere, all the time. The many worlds interpretation is controversial. Many physicists think it's too extravagant, multiplying universes beyond necessity. Others argue it's the most straightforward interpretation of quantum mechanics, taking the math seriously without adding extra assumptions about wave function collapse. The debate continues, but many worlds remains a serious scientific idea with substantial support. One interesting thing about the quantum multiverse is that it's different from the previous multiverse types. The Level 1 and Level 2 multiverses exist in space, scattered across infinite distances or separated by inflating regions. But the quantum multiverse doesn't exist in space. The different branches aren't located anywhere in our three-dimensional space. They're parallel realities, overlapping in some sense but unable to interact with each other. You can't travel to a quantum parallel universe. There's no distance to cross, no direction to go. The branches are separate in some more abstract sense, existing in what physicists call configuration space or Hilbert space, mathematical spaces that describe quantum states but don't correspond to physical locations. This makes the quantum multiverse even stranger than the others. It's not just that there are other universes far away. There are other universes overlapping with ours, existing simultaneously in the same space, but unable to interact, forever separated by the branching of quantum possibilities. There are other multiverse ideas beyond these three main types. Some physicists have proposed a Level 4 multiverse, sometimes called the mathematical multiverse, based on the idea that every logically consistent mathematical structure corresponds to a real universe. This is the most speculative and philosophical of the multiverse theories. The argument goes like this: our universe is described by mathematics. The laws of physics are mathematical equations. The properties of particles and fields are mathematical relationships. Everything we observe can be encoded in mathematical structures. But our universe's mathematics is just one possible mathematical structure among infinitely many. There are other mathematical structures, other systems of equations, other geometries and topologies and algebraic relationships. If mathematics describes reality, then perhaps every mathematical structure describes some reality, some universe where that mathematics is the law. This would mean there are universes with different numbers of dimensions, different symmetries, different fundamental structures, universes where time has multiple dimensions, or where space is discrete rather than continuous, or where logic itself works differently. Every mathematical possibility would be realized somewhere in some universe, creating a multiverse of unimaginable diversity. Most physicists are skeptical of this idea. It's extremely abstract and seems impossible to test even in principle. But it's an interesting thought experiment about the relationship between mathematics and reality, about whether math is something we invented to describe the universe or something we discovered that exists independently. Another multiverse idea comes from string theory, a theoretical framework attempting to unify quantum mechanics and gravity. String theory suggests that the fundamental constituents of reality are tiny vibrating strings of energy, and the properties of particles depend on how these strings vibrate. But string theory requires extra dimensions of space beyond the three we experience. These extra dimensions are curled up very small, invisible to us, but their exact configuration affects what physics looks like in our observable dimensions. And there are an enormous number of possible configurations, perhaps 10 to the 500th power different possibilities. Each configuration would give rise to different physics, different particle types, different forces, different constants. So string theory suggests a vast landscape of possible universes, each one corresponding to a different configuration of the extra dimensions. If all these configurations are realized somewhere, perhaps in different bubbles from eternal inflation, then we get a string theory multiverse with an almost unimaginable number of different universe types. How many universes are there total if we combine all these multiverse ideas? The question becomes almost meaningless because the numbers are so vast. Infinite in multiple ways, infinite copies in infinite space, infinite bubbles from eternal inflation, exponentially growing quantum branches, perhaps 10 to the 500th configurations in string theory, mathematical structures beyond counting. The total multiverse, if all these ideas are correct, would be so incomprehensibly vast and diverse that our universe is less than a grain of sand on a beach. It's utterly insignificant in the grand scheme, one tiny possibility among infinite possibilities, one brief branch in an infinite tree, one configuration in an infinite landscape. And here's where we'll pause in our journey. We've explored different types of multiverses, different ways that our universe might be just one among many. We've seen how these ideas emerge from serious physics, from inflation and quantum mechanics, and the fundamental nature of space and mathematics. And we've begun to appreciate just how vast existence might truly be if the multiverse is real. In the next part of our journey, we'll ask harder questions. Is there any evidence for the multiverse? Can we ever prove it exists? What does it mean for our place in reality if we're just one universe among infinite others? And can we find meaning and purpose in a multiverse where everything that can happen does happen somewhere? Those questions await us. But for now, rest here with what we've learned. The universe you know might be just the beginning. Reality might extend far beyond what you can see, far beyond what anyone can see, into realms of possibility so vast that they challenge our very concept of existence. You've traveled far in thought tonight, and there's more to come. But first, just rest. You've traveled far in thought tonight, and there's more to come. But first, just rest. So here we are, having explored the different types of multiverses that might exist. We've seen how infinite space could contain infinite copies of our universe. We've learned about bubble universes with different laws of physics, separated by eternally inflating space. We've discovered the quantum multiverse where every possibility branches into separate realities. And we've touched on even more exotic ideas like the mathematical multiverse and the string theory landscape. But now we need to ask a harder question, perhaps the hardest question of all. Is any of this real? Are these multiverses just interesting mathematical possibilities, fun thought experiments that emerge from our theories but don't actually exist? Or is the multiverse real, an actual feature of reality that we're part of whether we can observe it or not? This question matters because science is supposed to be about what we can observe and test. We develop theories, make predictions, perform experiments, and see if the predictions match reality. If they do, we gain confidence in the theory. If they don't, we modify or abandon the theory. This is the scientific method, the process that's given us our deep understanding of nature. But the multiverse seems to violate this fundamental principle. By definition, other universes are beyond our observation. We can't see them, can't visit them, can't interact with them in any way. So how can we ever know if they exist? How can we test multiverse theories if the other universes are forever beyond our reach? This is a serious objection, and many scientists use it to argue that the multiverse isn't really science at all. It's metaphysics, they say, philosophy disguised as physics. It's unfalsifiable, meaning there's no experiment that could prove it wrong, and unfalsifiable theories aren't scientific theories. They're just speculation, no better than any other untestable idea about reality. Other scientists respond that we shouldn't reject ideas just because they're hard to test. The multiverse emerges naturally from theories that we can test and that have been tested successfully. Inflation explains features of our universe that we can observe. Quantum mechanics has been verified by countless experiments. If these well-tested theories predict multiverses as a side effect, we should take that prediction seriously, even if we can't directly observe the other universes. It's like black holes before we had direct evidence for them. Einstein's general relativity predicted black holes, but for decades we couldn't observe them directly. They were theoretical predictions from a well-tested theory, and eventually we did find evidence for them through indirect observations. Now we've even photographed the shadow of a black hole and detected gravitational waves from colliding black holes. The predictions turned out to be real. Could the same thing happen with the multiverse? Could we find indirect evidence, some observation that would be difficult to explain without multiple universes? Some signature that points to the existence of other realities beyond our own? Some physicists think this might be possible, and they've been searching for such evidence. Let me tell you about some of the ideas they've explored. One place to look for evidence is in the cosmic microwave background radiation, that ancient light from when the universe became transparent about 380,000 years after the Big Bang. We've mapped this radiation in exquisite detail using satellites like the Planck spacecraft, and it shows tiny temperature variations across the sky, fluctuations that represent the seeds of cosmic structure. These fluctuations match the predictions of inflation theory very well. They have the right properties, the right statistical characteristics, the right pattern. This is strong evidence that inflation happened. But some researchers have looked for anomalies in the cosmic microwave background, unusual features that might hint at something beyond standard inflation. For example, If our bubble universe collided with another bubble universe in the distant past, it might have left a mark in the cosmic microwave background. The collision would create a kind of bruise, a circular pattern of temperature variations different from the normal random fluctuations. Several groups have searched for such collision signatures, analyzing the cosmic microwave background data, looking for circles or other geometric patterns that might indicate we bumped into another universe. So far, no convincing evidence has been found. There are some anomalies in the data, some features that don't quite match the simplest predictions, but nothing that clearly points to bubble collisions or other multiverse effects. The cosmic microwave background looks mostly like what we'd expect from standard inflation in a single universe. But the search continues. Future observations with more sensitive instruments might reveal something we've missed, or we might develop better theoretical predictions about what bubble collisions should look like, allowing us to search more effectively. The absence of evidence so far doesn't mean the multiverse is wrong. It just means we haven't found the smoking gun yet. Another type of evidence comes from the fine-tuning problem we mentioned earlier. Our universe appears to be precisely calibrated for life. Many fundamental constants have values that seem special, finely tuned to allow the existence of stars and planets and chemistry and complexity. Let me give you some specific examples to show just how precise this tuning is. Start with gravity. Gravity is much weaker than the other fundamental forces, and this weakness is crucial for allowing complexity to exist. If gravity were much stronger, stars would burn much hotter and faster, living only millions of years instead of billions. This wouldn't give life time to evolve. If gravity were much weaker, stars might not ignite at all, unable to compress their cores enough to start fusion. The exact strength of gravity seems to be set just right, within a narrow range that allows long-lived stars. Change it by more than a small percentage in either direction, and the universe becomes hostile to life as we know it. Or consider the strong nuclear force, the force that holds atomic nuclei together. This force has to be strong enough to bind protons and neutrons into stable nuclei, but not so strong that it makes atoms too stable. If the strong force were just a few percent stronger, protons would bind together so readily that hydrogen would be rare. All the hydrogen in the early universe would have fused into heavier elements, leaving no hydrogen for stars to burn or for water molecules to form. If the strong force were a few percent weaker, nuclei would be less stable. Only the simplest elements would exist. No carbon, no oxygen, no complex chemistry, no molecules capable of storing information or building complex structures. Again, the strong force appears to be finely tuned, set to a value in a narrow range that allows both simple and complex elements to exist. Or look at the electromagnetic force, which governs how charged particles interact. The strength of this force determines how tightly electrons are bound to nuclei, which affects the size of atoms and the nature of chemistry. If electromagnetism were stronger or weaker by more than a small amount, chemistry would work differently or might not work at all in any way we'd recognize. Or consider the difference between the masses of the proton and neutron. They're very close, differing by only about 1 part in 1,000. But this small difference is crucial. If the neutron were lighter than the proton, neutrons would be stable and protons would decay into neutrons. There would be no atoms, just a universe full of neutrons. If the mass difference were much larger, nuclear fusion in stars would work differently, changing which elements could form. These are just a few examples among many. Again and again, when physicists examine the fundamental constants of nature, they find that life seems to require a very specific set of values. Change almost any constant by more than a small amount, and the universe becomes lifeless and boring, unable to support the kind of complexity needed for life or intelligence or anything interesting at all. This fine-tuning is puzzling. Why are the constants set to these special values? Is it just luck? Did we win in cosmic lottery, getting a universe that happens to be life-friendly purely by chance? That seems unsatisfying, especially when the odds appear to be so astronomically small. Or is there some deeper reason? Maybe the constants aren't really free parameters. Maybe they're determined by some deeper theory we haven't discovered yet, some underlying principle that requires them to have these values. This would explain the fine-tuning, but so far, no one has found such a principle. The constants seem arbitrary in our current theories. The multiverse offers a different explanation. If there are vast numbers of universes with different constants, then most of them are indeed lifeless and boring. But some, purely by chance, have constants in the narrow range that allows complexity and life. We find ourselves in one of those rare universes not because it's objectively special, but because we couldn't exist anywhere else. This is the anthropic principle in action. We observe a life-friendly universe because that's the only type of universe we could observe. It's a selection effect. Just as fish will always find themselves in water rather than in deserts, conscious beings will always find themselves in universes that permit consciousness. The universe isn't fine-tuned for us. Rather, we exist in one of the rare universes that happens to be compatible with our existence. This explanation only works if the multiverse is real. If there's only one universe, then the fine-tuning remains deeply mysterious, perhaps requiring some kind of creator or designer to set the constants just right. But if there are countless universes with different constants, then the fine-tuning is explained naturally through selection. No designer needed, just vast numbers of universes trying out different possibilities. So the fine-tuning of constants can be seen as indirect evidence for the multiverse. It's not proof, of course. Maybe there is a deeper theory that explains why the constants have their values. Maybe there's some other explanation we haven't thought of, but the multiverse provides a simple, elegant explanation for something that otherwise seems inexplicable. Now let's think more carefully about this anthropic principle, because it's subtle and easy to misunderstand. There are actually different versions of the anthropic principle, and they say different things. The weak anthropic principle simply observes that we must find ourselves in a universe compatible with our existence. This is almost tautological, a truism. Of course, we're in a universe where life is possible. If we weren't, we wouldn't be here to observe anything. This version doesn't really explain anything. It just points out a selection effect. But the weak anthropic principle combined with the multiverse becomes more powerful. If there's only one universe, saying we must observe it to be life-friendly doesn't explain why it is life-friendly. It's like being dealt a royal flush in poker and saying, well, someone had to get these cards. True, but it doesn't explain why you got such improbable cards. However, if millions of hands are being dealt simultaneously to millions of players, then it's not surprising that someone somewhere gets a royal flush. And if you happen to be that someone, you shouldn't be too amazed. You were only going to notice if you got good cards. The other millions of players with bad hands exist too, but they're not as excited. The multiverse is like millions of poker games happening at once. Most universes get bad hands, constants that don't allow life. But some get good hands, constants in the right range. We're in one of the lucky universes, and we shouldn't be too surprised because we could only find ourselves in a lucky universe. This is the weak anthropic principle made powerful by the multiverse. It transforms from a tautology into an actual explanation for fine-tuning. There's also something called the strong anthropic principle, which makes bolder claims. It suggests that the universe must have properties that allow life to develop because the universe somehow needs observers. Without consciousness to observe it, the universe wouldn't really exist or wouldn't have meaning. This strong version gets into murky philosophical territory, mixing physics with metaphysics in ways that make many scientists uncomfortable. It sounds almost mystical, suggesting that consciousness plays a fundamental role in reality. Most physicists prefer the weak anthropic principle, which just points out selection effects without making grand claims about consciousness being necessary for existence. But there is an interesting connection to quantum mechanics here. Remember the measurement problem in quantum mechanics, how observation seems to collapse superpositions and determine outcomes. Some interpretations of quantum mechanics give observers a special role. Maybe conscious observation really does affect reality in some way. And if so, maybe universes that don't develop observers are somehow less real or less fully actualized than universes that do. This is highly speculative, bordering on philosophy rather than science. But it's an interesting thought. In the many worlds interpretation, all possible outcomes happen, creating vast branching trees of universes. But maybe the branches with observers, with consciousness to experience them, are somehow privileged or more significant than the empty branches where nothing ever wakes up to notice its own existence. We're venturing into deep philosophical waters here, and we don't have definitive answers. But these are the kinds of questions the multiverse raises, questions about the relationship between consciousness and reality, about whether existence requires observation, about what it means for something to be real. Let's shift to another fascinating idea related to the multiverse, one that's captured popular imagination in recent years. The simulation hypothesis, the idea that we might be living in a computer simulation created by some advanced civilization. This might sound like pure science fiction, but some serious thinkers have argued it's actually quite plausible. The argument goes like this: if it's possible to create realistic simulations of conscious beings, and if civilizations eventually develop the technology to do this, and if such civilizations create many simulations, then most conscious beings would be simulated rather than real. Think about it. Our civilization is already creating increasingly sophisticated simulations. We build virtual worlds in video games, populate them with characters that behave in complex ways. Our simulations aren't conscious yet, at least not as far as we can tell, but they're getting more sophisticated every year. Now imagine our technology continues advancing for thousands or millions of years. Eventually, we might be able to create perfect simulations, virtual worlds with simulated conscious beings that are indistinguishable from real ones. These simulated beings would think they're real, would believe they're living in a physical universe, would have no way of knowing they're just patterns of information. running on some advanced computer. And if we can create such simulations, we'll probably create many of them. Maybe billions or trillions of simulations, each one containing billions of conscious beings. For every one real human, there might be trillions of simulated humans. Now, if you're a conscious being and you don't know whether you're real or simulated, what should you conclude? Just based on the numbers, you should think it's far more likely that you're simulated. If there are trillions of simulated beings for every real being, the odds are overwhelmingly in favor of you being one of the simulated ones. This is a version of the anthropic principle applied to simulations. We might want to believe we're real, but if most conscious beings are simulated, we're probably simulated too, just by the statistics. This argument has some holes in it. Maybe it's not possible to create conscious simulations. Maybe consciousness requires something that can't be simulated. Some physical process that only happens in biological brains, or some quantum effect that classical computers can't reproduce. If true, then the whole argument collapses because no civilizations could create conscious simulations. Or maybe civilizations that develop simulation technology choose not to use it, perhaps for ethical reasons. If you can create conscious simulations, you're essentially creating sentient beings who might suffer, who might experience pain and fear and confusion without understanding they're simulated. Many civilizations might decide this is unethical and refuse to create such simulations, leaving the number of simulated beings much lower than the argument assumes. Or maybe civilizations that could create simulations destroy themselves before doing so, wiped out by war or environmental collapse or artificial intelligence or some other existential risk. If most civilizations don't survive long enough to develop advanced simulation technology, then again, the number of simulated beings would be much lower. But if none of these objections hold, if conscious simulations are possible and commonly created, then the simulation argument has force. We might really be living in a simulation, our entire universe just a sophisticated computer program running on hardware and some higher reality. What would this mean for the multiverse? Well, if we're in a simulation, there could be many other simulations running on the same hardware or on different computers. Each simulation would be its own universe, its own reality from the perspective of the beings inside it. This would give us yet another type of multiverse, a multiverse of simulated realities stacked in layers. And here's a mind-bending thought. If we're in a simulation, and if our simulators are also in a simulation created by an even more advanced civilization, and if that civilization is also simulated, you get an infinite regress of nested simulations, universes within universes within universes, turtles all the way down. At some point, there must be a base reality, a real universe that's not simulated, where the hardware actually exists physically. But we might be many layers removed from that base reality, living in a simulation of a simulation of a simulation. And we'd have no way of knowing how many layers deep we are. Is there any way to test whether we're in a simulation? Some people have suggested looking for glitches, inconsistencies in the laws of physics, places where the simulation breaks down or shows its artificial nature. Maybe we'd find pixels at small enough scales, discrete chunks of space and time rather than smooth continuity. Maybe we'd find limits on computational resources, places where the simulation cuts corners to save processing power. But a sufficiently advanced simulation probably wouldn't have obvious glitches. The simulators would make it seamless, or they'd program the simulated beings to not notice inconsistencies, or they'd intervene to patch problems before anyone detected them. Finding proof of simulation might be as difficult as finding proof of other universes in the multiverse. The simulation hypothesis, like the multiverse, might be unfalsifiable. We might never know for certain whether we're real or simulated, and in some sense it might not matter. If the simulation is perfect, if our experiences are real to us, if we have genuine consciousness and feelings and thoughts, then does it really make a difference whether we're running on biological hardware or silicon chips or something else entirely? This brings us to deep questions about the nature of reality and existence. What does it mean for something to be real? Does reality require some kind of fundamental physical substrate, or is any sufficiently complex information pattern real regardless of what it's running on? These questions connect to both the multiverse and the simulation hypothesis. In the many worlds interpretation of quantum mechanics, are the other branches real even though we can't interact with them? In a multiverse of bubble universes, are the other bubbles real even though we can't observe them? In a simulation, is the simulated world real even though it's ultimately just information? Different people give different answers. Some say reality requires direct observability. If we can't interact with something in any way, it's not real, just a theoretical construct. Others say anything that exists mathematically or informationally is real, regardless of whether we can observe it. The pattern of information that makes up your consciousness is real whether it's running on neurons or on computer chips or on some substrate we haven't imagined. There's no definitive answer. These are philosophical questions as much as scientific ones, but thinking about them helps us understand what the multiverse really means and what's at stake in deciding whether to believe in it. Now let's think about some of the strange paradoxes and implications that arise if the multiverse is real, particularly if space is infinite and contains infinite copies of everything. If the multiverse contains infinitely many regions with every possible configuration of matter, then there are infinitely many copies of you scattered throughout. Not just similar people, but exact copies down to the atomic level. People with identical memories, identical thoughts, identical experiences up to this moment. These copies would be you in every meaningful sense. They'd have your personality, your history, your relationships, everything that makes you you. And they'd be living lives identical to yours, making the same choices, having the same experiences, thinking the same thoughts right now. But here's where it gets strange. Since there are infinitely many such copies, there would also be copies that are slightly different. Copies where you made a different choice at some point in the past, leading to a different life trajectory. In some regions, you chose a different career. In others, you married a different person or never married at all. In others, you were never born because your parents never met. Every possible version of you exists somewhere if the multiverse is infinite. Every choice you could have made, you did make in some other region. Every path your life could have taken, it has taken somewhere. There are versions of you living your dream life and versions living your worst nightmare and everything in between. This raises bizarre questions about identity and responsibility and meaning. If every choice leads to a universe where you made that choice and another where you made the opposite choice, do your choices really matter? You're going to experience all outcomes anyway, in different branches or different regions. There's a you who succeeds and a you who fails at whatever you're trying to do. Some people find this liberating. It means you can't really fail because there's always a version of you who succeeded. It means you don't have to stress about decisions because all options get explored in different universes. You're guaranteed to live every possible life eventually, experiencing everything that could happen to someone with your starting conditions. Other people find it disturbing or meaningless. If all outcomes happen, what's the point of trying? Why make good choices if there's a universe where you made the bad choice and have to live with those consequences? Why care about anything if your actions don't really determine which branch or region you end up in? But I think this reaction misses something important. Even if all possible versions of you exist across the multiverse, you only experience one path through reality. You're on one branch in one region, living one life. The other versions are you in some abstract sense, but you don't have access to their experiences. You only live your life, make your choices, face your consequences. So your choices do matter to you in your branch of reality. The fact that other versions of you made different choices doesn't diminish the importance of your choices for your own experience. You still have to live with the outcomes of what you decide. It's like how the existence of other people doesn't make your life meaningless. Yes, there are billions of other humans living their lives, experiencing their own joys and sorrows, but that doesn't make your experiences less real or less important to you. You still have to live your life, and what happens to you matters to you regardless of what's happening to other people. The multiverse is similar, but more extreme. Instead of billions of other people, there might be infinitely many other versions of you, but the principle is the same. Their existence doesn't erase the reality of your experience or the importance of your choices for your own life. Another strange implication of an infinite multiverse. Anything that can happen will happen infinitely many times. Not just likely things, but also incredibly improbable things. Rare coincidences, unlikely events, things we'd normally dismiss as impossible. For example, quantum mechanics allows for the possibility, however absurdly unlikely, that all the air molecules in a room could randomly move to one corner, leaving a vacuum in the rest of the room. The probability is so low that it would never happen in the entire history of our universe. But in an infinite multiverse, it must happen somewhere, infinitely many times. There are regions where the air spontaneously evacuates from rooms, suffocating people for no apparent reason. Or consider even more bizarre possibilities. Quantum fluctuations could, with vanishingly small probability, assemble themselves into complex structures purely by chance. A functional computer could pop into existence randomly. A human brain could form spontaneously from random particle motions. These things have non-zero probability according to quantum mechanics, so they must happen somewhere in an infinite multiverse. This leads to something called Boltzmann brains, named after physicist Ludwig Boltzmann. A Boltzmann brain is a hypothetical, self-aware entity that arises from random fluctuations rather than through evolution. In an infinite multiverse, there should be infinitely many Boltzmann brains, conscious minds that pop randomly into existence for brief moments before dissolving back into chaos. This creates a strange problem. If Boltzmann brains vastly outnumber normal evolved brains like ours, then we should expect to be Boltzmann brains. We should expect to have false memories, to be experiencing a brief hallucination before ceasing to exist, rather than being real, evolved beings with genuine histories. The fact that we seem to have consistent, reliable memories and that the universe seems to follow orderly laws suggests we're not Boltzmann brains. But if Boltzmann brains are common in the multiverse, this reasoning becomes circular and confusing. It's a genuine puzzle in multiverse theory, one that physicists are still trying to resolve. These kinds of paradoxes show that the multiverse raises deep conceptual problems. It's not just about whether other universes exist. It's about what existence means, what probability means when everything possible happens somewhere, what we should expect to observe given different multiverse models. Let's turn now to the question of what we can actually know about the multiverse and what might be forever beyond our knowledge. This is crucial because science is fundamentally about knowledge, about figuring out what's true about reality through observation and reasoning. Traditional science works like this. You develop a theory that makes predictions. You design experiments or observations to test those predictions. If the predictions match observations, the theory gains credibility. If they don't match, you modify or reject the theory. This process of testing predictions against observations is how science makes progress. But the multiverse challenges this process. If other universes are by definition beyond our observation, how can we test multiverse theories? What predictions do they make that we can actually check? Some multiverse ideas do make testable predictions about our universe. Inflation, which leads to the bubble multiverse, makes predictions about the cosmic microwave background radiation, about the geometry of space, about the distribution of galaxies. These predictions have been tested and match observations well, giving us confidence that inflation is correct. If inflation is correct, then eternal inflation and bubble universes are likely consequences. So in some sense, we have indirect evidence for the bubble multiverse, even though we can't observe other bubbles directly. The theory that predicts them also predicts things we can observe, and those predictions are confirmed. Similarly, quantum mechanics makes countless testable predictions that have been verified to extraordinary precision. If quantum mechanics is correct, and if the many worlds interpretation is the right way to understand it, then the quantum multiverse exists. We can't observe the other branches, but we can test quantum mechanics itself, and the theory that implies many worlds has passed every test we've given it. This is how multiverse theories can be scientific even if the other universes are unobservable. They're consequences of theories that are testable and well confirmed. If you believe the theory, you should believe its consequences, even the unobservable ones. But this only works if the multiverse is a necessary consequence of well-tested theories. If the multiverse is just one possible interpretation among many, or if it requires additional assumptions beyond what's needed to explain observations, then the argument is weaker. For example, many worlds is one interpretation of quantum mechanics, but there are others. The Copenhagen interpretation, spontaneous collapse theories, pilot wave theories, and others all explain the same observations without requiring parallel universes. So you can accept quantum mechanics without accepting the many worlds multiverse. Similarly, inflation might not require eternal inflation. Maybe there are versions of inflation that don't lead to bubble universes. If so, we can't claim the bubble multiverse is a necessary consequence of tested theory. This is where the debate gets contentious. Advocates of the multiverse argue that their versions are the simplest or most natural interpretations of well-tested theories. Critics argue that the multiverse requires extra assumptions and shouldn't be believed without direct evidence. The debate isn't settled and probably won't be settled soon. It requires judgments about what counts as a simple theory, what counts as a natural assumption, what level of evidence we should require for believing in unobservable entities. Different scientists make different judgments, leading to different conclusions about the multiverse. But here's something important to understand. Even if we can never observe other universes directly, the multiverse hypothesis isn't completely unfalsifiable. We could potentially falsify it by showing that the theories it's based on are wrong. For example, if future observations showed that inflation didn't happen, that would undermine the bubble multiverse. If we found violations of quantum mechanics, that would undermine the many worlds multiverse. So there are ways the multiverse could be proven wrong, even if it can't be proven right through direct observation. This is weaker than ideal scientific testability, but it's not nothing. It means the multiverse is constrained by evidence, even if not directly proven or disproven by it. There's also the possibility that we might find more direct evidence someday. Maybe we'll detect signatures of bubble collisions in the cosmic microwave background. Maybe we'll find some other observable consequence of other universes that we haven't thought of yet. Science is full of surprises, and what seems unobservable today might become observable tomorrow with new technology or new theoretical insights. So we shouldn't completely dismiss the multiverse as unscientific. It's on the frontier of science, pushing the boundaries of what we can know, raising difficult questions about evidence and testability. But it's connected to real physics, to theories that have been tested and confirmed, to observations that need explaining. As we near the end of our journey, let's reflect on what all of this means for how we understand our place in reality. The multiverse, if real, would profoundly change that understanding. In a single universe, we could think of ourselves as potentially special, unique, perhaps the only conscious beings in all of existence. Even if we're just on one planet among trillions, even if the universe is vast and we're tiny, we could still be the only part of that universe that woke up to contemplate its own existence. But in a multiverse, especially an infinite one, we're guaranteed not to be special or unique. Everything that can exist does exist somewhere. Every possibility is realized. We're just one tiny piece of an infinite whole, utterly unremarkable on cosmic scales. Some people find this depressing. It seems to diminish us, to make us insignificant, to suggest that nothing we do matters because it's all happening somewhere anyway. We're not special. We're not unique. We're just one instance among infinite instances, one drop in an infinite ocean. But I think there's another way to see it, a perspective that's actually comforting and meaningful rather than depressing. Yes, in the multiverse you're not unique, but you're still real. Your experiences are genuine. Your consciousness is actual. Your life matters to you and to the people you interact with. The existence of other versions of you doesn't diminish the reality of this version, the one you're actually experiencing. Think of it this way. You already know there are billions of other humans, each living their own life. Does that make your life meaningless? Does the existence of other people diminish your experiences or your relationships? Of course not. You still live your life. You still care about things. You still have goals and dreams and fears and joys. The multiverse is just an extension of this. Instead of billions of other people, there might be infinite other yous. But the principle is the same. Their existence doesn't erase yours or make it less real. You're still you, still living your one life, still making your choices, still experiencing your unique path through reality. And there's something beautiful about being part of a vast multiverse. It means existence is richer, more diverse, more full of possibilities than we ever imagined. It means reality isn't just this one universe, but something far grander, something that includes every possibility, every potential, every version of what could be. In a multiverse, nothing is wasted. Every possibility gets explored. Every potential gets realized. Every story that could be told gets told somewhere. The multiverse is complete in a way that a single universe could never be. And you're part of that completeness. You're one of the infinite possibilities that got actualized, one of the infinite ways that matter and energy and consciousness can organize themselves. You're a unique thread in an infinite tapestry, a unique note in an infinite symphony. Does your thread matter to the tapestry? Does your note matter to the symphony? On one level, no. Remove one thread and the tapestry is still there. Remove one note and the symphony continues. But on another level, yes, the tapestry wouldn't be complete without every thread. The symphony wouldn't be whole without every note. You're both insignificant and essential. Insignificant because you're one among infinite. Essential because the multiverse wouldn't be complete without you, without your particular pattern, your particular experience, your particular path through possibility space. This is a paradox, but it's a beautiful one. The multiverse makes us smaller and larger at the same time. Smaller because we're not unique or special. Larger because we're part of something infinitely vast and infinitely diverse. And here's a final thought as we close this journey. We may never know for certain whether the multiverse is real. It might remain forever in the realm of theory, a fascinating possibility that we can't definitively confirm or deny. We might die without knowing the answer, leaving it for future generations to discover or leaving it permanently unknowable. But the question itself is valuable, asking whether we're alone in reality, whether our universe is all there is, or just one among many. This is one of the deepest questions conscious beings can ask. It's a question about the nature of existence itself, about how much reality there is, about what possibilities are actualized, and which remain merely potential. Even if we never answer it conclusively, thinking about it expands our minds. It helps us see beyond our immediate experiences, beyond our planet and our galaxy and our universe, into realms of possibility that challenge everything we thought we knew about reality. And perhaps that's enough. Perhaps the value of the multiverse isn't in knowing for certain whether it's real, but in the journey of thinking about it, of imagining it, of confronting what it would mean if it's true. The questions matter as much as the answers, maybe more. So as you drift toward sleep tonight, let these questions rest gently in your mind. How many universes are there? Is reality just what we see, or does it extend infinitely beyond our horizon? Are there other versions of you living different lives in parallel realities? Is the multiverse real, or is it just a beautiful mathematical dream? We don't know. We may never know. But the possibility is there, vast and strange and wonderful. And you've spent time tonight contemplating it, expanding your sense of what reality might be. stretching your imagination to encompass possibilities that go far beyond everyday experience. The multiverse, whether real or imaginary, is a gift to consciousness. It gives us something profound to think about, something that puts our lives in perspective while also affirming their reality and importance. We're tiny but real, insignificant but essential, one among infinite but still absolutely ourselves. Rest now in that paradox. Let the vastness of possibility wash over you without overwhelming you. You're part of something immense, whether it's one universe or infinite universes. And your part matters, your experience is real, your consciousness is valuable. The question of how many universes exist may never be answered, but you exist here and now in this universe, in this moment. And that's certain, that's real, that's enough. Sleep peacefully, knowing you're part of reality, whatever reality ultimately turns out to be. The multiverse may be infinite, but your experience of it is singular, unique, irreplaceably yours. Good night, traveler through possibility space. Rest well. Dream of infinite universes, or dream of nothing at all. Either way, you've journeyed far in thought tonight. The answer to how many universes there are remains unknown, but the question has been worth asking, and your consciousness pondering these mysteries is itself a kind of miracle, whether it occurs in one universe or infinite. Sleep now. The multiverse, real or imagined, will still be there tomorrow. Tonight is for rest. Good night.